say, hey, I want to move this force, I'm the force, from here to here. Can I do that? Yeah. It's the lateral transfer theorem. What's it say? In order to do that, I move the force and add a compensating moment. Next. Yeah. Varignon's theorem. It's not Varignon. It's Varignon. He's French. Varignon's theorem says, hey, whether you use the components or the force itself to find moments doesn't matter. You get the same result. So if it's easier to do a moment by taking the components of the force, by all means, go ahead and do so. Next concept. Yeah. Newton's third law: for every action, there's an equal and opposite reaction. Action. I ain't studying for this goddamn class. Reaction, I give you an M. See, it works. Next. Give me another one. Yeah.
Equivalence.
Huh?
Equivalence.
Oh! Wow. Equivalence. What the hell is equivalence? By the way, if anybody asks you, what are the two biggest concepts you learn in statics? You're going to say equilibrium and equivalence. Those are the biggies. What's equivalence say? Equivalence says I can take any force, any moment, or a system of forces and moments. I don't care how many there are. 5,000 forces, 10,000 moments. Don't give a shit. I can always get it down to a single force, single moment. And in special cases, and we're going to learn the 3 special cases when we get there in chapter 4, where I can reduce it down to a single force at a known location. Give me another concept. By the way, you have seen equivalence in action already in Physics 1, and you didn't even know it. Oh, shit. Where did you see it in Physics 1? Do you remember Physics 1? Hell no. I guarantee you don't remember Physics 1. But you saw equivalence in Physics 1, but you didn't know it. You know why? Because the teacher didn't emphasize the concept behind it. Here's the equation, fucking memorize it. That's not learning. Learning is understanding. Learning is being able to answer why. If you can't answer the why, you didn't learn shit. Where did you learn equivalence? You learned it when you wrote the center of gravity equation. How many remember writing the center of gravity equation in Physics 1? Do you know what it is? Say it again slowly. Hold on. Are you comfy? I should get you a lazy one. You need to be more comfy. Go ahead. Say it loud so they can hear it.
Take each mass at each point multiplied by how far away it was from a given point, and then you divide by the point.
Everybody hear that? Everybody heard that? How many remember that now that she said it? Now let me ask this question. Do I have to use mass or can I use weight? What do you think? I don't know. Shit. You can use mass or weight. Now, honestly, this is what she's saying. Let me write it out for you. Because you should be able to see it, so maybe you can understand it. What she said was this. Hey, if I want to know the X bar, where they're located. Oh, there we go. She's saying take W1 times X1 plus W2 times X2 plus W3 times X3, blah, blah, blah. Divide this by W1 plus W2 plus W3. That's what she said. Now, can I use mass? Sure, because the relationship between mass and weight is what? W is equal to mg. Right? So if I take the weights divided by g, I get m. And if you have W over g in the numerator, W over g in the denominator, the g's are going to cancel out. That's just for math. Right? W total, that's the sum of these guys, times x bar is equal to W1 x1 plus W2 x2 plus W3 x3. Yes? Somebody please tell me what W1 x1 really represents. Now, what I'm asking you is understand the equation. W1 x1 really represents what? I don't know. A what? Yes. Force, weight is a force, times a distance, x1, force times a distance. That's the moment. Oh, crap. So I'm saying, hey, the moment of the reduced system equals the moment of the original system. So this is what I have. Here's the reduced system, W total at sum x bar. This is equivalent to W1, W2, W3, where this is x1, that's x2, that's x3. So what is really the center of gravity equation? Hey, moments of the original system, W1, x1, W2, x2, W3, x3, must equal to the moments of the reduced system. Well, that's exactly what the hell equivalence says to do. So when you wrote the equation for center of gravity, you were literally applying equivalence concept. You were saying the moments of the original system must equal the moments of the reduced system. Do I really have to remember that equation now? No, I just got to remember, hey, it's an application of equivalence, or the reduced system moments equal the original system moments. Period. End of discussion. I don't have to memorize the equation anymore. If you understood the concept. But in Physics 1, you weren't taught the concept. Memorize the goddamn equation and use it. It's not learning. Give me another concept. Another concept. Yes! Superposition. You use this in engineering all the time. You've actually used this a lot already in your life. I give you a rectangle. I give you a triangle. I give you a cutout circle. And I tell you, find me the area. Well, you'd find the area of the rectangle. You'd find the area of the triangle. You'd find the area of the circle. Add the rectangle, the triangle, and subtract out the area of the circle. You'd find the area of the whole figure, correct? What I just did was I superimposed a rectangle, triangle, and a circle to get my final answer. I just superimposed three things to get my answer. You've done this even back in frickin' probably middle school. You weren't, it wasn't called superposition, but that's what it's called. You're going to use superposition in here, you're going to use it in dynamics, you're going to use it in electrical systems, you're going to use it in mechanics, materials, everywhere. Next, give me another concept. Another concept. Oh, you're going for two. Go ahead. Oh, come on. Because nobody else wants to talk. Area moment. What the fuck is area moment of inertia?
1.
It's a stiffness parameter based on the shape of the figure. There's two stiffness parameters in engineering. One is based on material, which is Young's modulus of elasticity. And one is the area moment of inertia based on shape. What is the most efficient shape that engineers use all the time? The what?
Triangle.
Not the triangle.
Why don't you-
Huh?
I can't read.
No. Fuck the sphere. What do you think the most efficient?
It's a W. It's a W.
Not the square socks.
This one. You just want this one?
Not the triangle.
This one?
The
Or are
ivy.
you playing it?
The I-beam is a configuration that has, for any given area, the largest I value you can get. Do I really want the largest I value? Yes, because every structural equation has the I value in it, and it's always in the freaking denominator. Think about this. I have a numerator, I have a denominator. The number in the denominator, as I make that bigger and bigger and bigger and bigger, what happens to the ratio? It gets smaller and smaller and smaller. So the stresses the deflection all goes small if I create a huge I value, because I is in the denominator. I don't know anything about I, but I do know I need to make it big. Give me another concept. Come on. Yes. Hey. You already said that. Parallel. What is the parallelogram rule? Forgot. What? You can't even tell me the name of what I got? Come on, man. Let me ask this one. Wait a second. Let me ask this question. When I find the component, is that a vector or a scalar? Huh? It's a scalar. So think about what you tried to do in physics. Let me go up here so I can show it to you. Here's what you tried to do in physics. You said, I've got this x, y, I've got this force, which is 100, angle 30 degrees. You proceeded to find this component fx and that component fy. This component was 86.6, this component was 50. Agreed? How'd you do that? I did that because I said, hey, cosine of 30 is adjacent over the hypotenuse. Adjacent is fx, the hypotenuse is 100. Rearrange, fx is 86.6, because cosine of 30 is 0.866 times 100, that's 86.6. Same thing with the fy. I said sine of 30 degrees is fy over the hypotenuse. I'm using SOHCAHTOA, which is sine 30 is half of 150. Now, here's what you want to do. I'm going to say f is equal to 86.6 plus 50. That's what I want to do. I have a problem. What's the problem? I got vector over here and then scalars over here. So we human beings came up with the, you know what? I know 86.6 along the x. So I'm going to create a unit vector that I'm going to call I that is always pointing along the x. Now the question I have for you is, why the hell do we use a unit vector? Why can't I just use any old vector that points along the x? Why the unit vector? Because here's what I want to do. I want to take and multiply this by I. I, we said, is a unit vector. What's its magnitude? 1. What's 1 times 86.6? Doesn't change the value. That's why you're multiplying by a unit vector. I don't want to change the value of 86.6. So I got to multiply by a magnitude of 1. And what I'm doing is, please notice, there's my magnitude, there's my direction, and there's my parallelogram rule where I've added the two components at the tail. Vector satisfied. So why are you using IJK? Because I want to express vectors on the left to vectors on the right. So now I come in and I write J here, where J is a unit vector that always points along the y-axis. Yes? This is why you used IJK. Because I want to express vectors equals vectors, and I can't when I do components. Because components are freaking scalars. So how do we, human beings, get around that dilemma of saying vectors equal scalars? Well, vectors can't equal scalars. So I'm going to say vectors equals vectors. How do I accomplish that? Multiply each number by a unit vector along the specific axis. Along the x, I. Along the y, j. Along the z, k. And that's why you use IJK. You with me? Who's not with me? Now, moving on. We should have, how many have seen the a video on vectors? Not many. What the hell are you doing? You're already behind. We haven't even started yet. In that video, you should have, how many have seen it? All right, so tell me, what's the major theme in that video? What? Which is called what? No. What? Yeah.
So basically, kind of sexuality is usually the opposite of the vector.
That's not the whole theme. What's the theme of this whole frickin' lecture? Two things. One, find me a resultant. How do I find a resultant? Add F1 plus F2 to get a resultant. Yes? How do I accomplish that? I use the parallelogram rule. Head to tail addition of the vectors. Right? Now, to your point, hey, how do I subtract vectors? Well, I say A plus a negative B. What's a negative B vector? Well, if the vector is this way, negative B points it the other way, flips the arrow. Yes? So, the first part of this whole thing was, hey, get me a resultant. Well, technically, what the hell is a resultant? What are we doing? By the way, what does it mean to have a resultant? What's a resultant, please? Yes. Yes. Now, what's the significance of that final vector? It has the same net external force as the two it replaced, or the three or the four, or whatever. So I took vector A, vector B, replaced it by a single resultant, single force that I call the resultant. What's the significance of the resultant? Hey, it has the same net external effect on the body that the other two forces it replaced did. So the body sees one force in the reduced system. In the original system, it sees two forces. It can't tell the difference between two forces and one force externally. Internally, all bets are off. Yes? So, what about if I have three forces? What the hell do I do then? Well, if I take and add everything head to tail, I won't get a nice neat triangle, I'll get a polygon. Well, shit, I don't know how to deal with polygons. What do I do? Panic, cry, call a teacher names? No. You can. It'll satisfy you for a little bit that you called me a name, but you didn't solve the problem. What do I do? Go ahead. Yes! Break it up into smaller triangles. What do? I take vector 1, vector 2, get a resultant. Take that resultant, add it to the vector 3. Get another resultant. Add the fourth vector to that resultant to get another damn resultant. So all I'm doing is just piecemealing it, triangle after triangle after triangle after triangle in order to get the final result. Yes? Now, if you had seen the video, this would all make more sense. Okay, that's the result. That's the number one theme of that lecture video. What's the second theme of that lecture video? Huh? What is it? Resolution. Well, what the hell is a resolution? Oh boy. Go ahead, tell me what's resolution. Yes, it's the opposite of finding the resultant. So this time, I give you the result and say, hey, break this down into two forces. So the forward running problem is, given two forces, finding the resultant. The backwards problem, the reverse problem is, I give you the resultant, give me the two forces that led to that result. That's a resolution problem. How many ways can I resolve a force? Oh shit, what is it? You saw the video. Fantastic. Repeat that for me. There's an infinite number of ways to do that. Oh shit, there is, yes. However, engineers like two methods. What are those two methods? So there are two things that engineers like to resolve into. What are those? Go ahead, give me one.
Line of action.
Yes, when I have a resultant, but I know the line of action of those components in essence. So when I know the two lines of action, I can resolve along those two lines of action. Give me another one. There's two of them. What? When I know one of the two components. Classic problem, just so you're aware, the classic problem is this. I have here's A, here's B, here's C. And I tell you, hey, I want to know how much of that 100 pounds is being taken up by member BC and how much of it is being taken up by member AB. And you say, well, why the heck do you want to know that? Well, I need to know what the forces are in BC and AC so I can construct it. The first step is finding these forces. Then you got to decide, hey, do I make it out of steel, wood, aluminum? What do I make it out of? And do I make it out of tubular? Do I make it triangular? Do I make it the members rectangular? Those are decisions you can't do in this class. You need to go to the next class in order to make that decision. All I can teach you here is how to get the forces along BC and AB. That is a resolution problem along two lines of action. The two lines of action being BC and AB. So when we talk about resolution, this is what we're trying to tell you. Hey, give me the forces that are associated with BC and AB. Is it 50-50? Is it 60-40? Is it 75-25? I don't know. That's why I have to calculate. That's why I have to go down and do some math. Oh, math? Yes, unfortunately, that's what engineering is all about. Besides the concepts, you got to do math. If your math sucks, you need to brush up. And, in my opinion, most of your math sucks. That's why I gave you a math review to do. That's due when? Friday at midnight.
Midnight.
Okay? So all that math that I'm giving you is math you should be able to do. You should have covered this technically back in high school for the most part. Unless there was some derivatives, and I don't remember. Was there any derivatives in there? Okay, so maybe your first calculus class that you took. Well, how some of you took calc in high school, didn't you? How many took calculus in high school? Okay, so I'm not asking you anything you should be able to do. Now, whether you remember or not, that's a whole different ballgame. Right? True, false. Vector addition is associative. Vector addition is commutative. In other words, whether I say A plus B or B plus A, it doesn't matter. Vectorially, it doesn't matter. Right? Now, the last thing, so notice, resultant, resolution, those are the two big themes. How do I get a resultant? I add vectors by using the parallelogram rule. So, here's a question for you. When applying and finding a resultant, right? How many concepts of the 12 concepts did you use And what were they? Ooh. Good. You see how I make up quizzes? This is a prime example of how I make up a quiz. Question. When you did resultant, A, how many concepts did you use and what were they? So, this would be a quiz question. What are you going to do? I don't know. Maybe I should look over here and see what she does. That would be called cheating. That would be bad. I caught somebody cheating last semester. Double left them. Don't do it. And by the way, it's very easy to see who the cheater is. You know why? Your body language gives you away. It clearly gives you away. Holy shit, does it give you away. A cheater's body language is very distinct from a student that is just doing the problems. I've mastered the art of looking at students and deciding who's cheating and who's not. And you know when I start deciding who cheats and who doesn't? Tomorrow, when I give you the first quiz. If you're going to cheat on the quiz, I guarantee you're going to cheat on the test. So my first look is tomorrow to see and pinpoint who might be cheating. And I'm not the type that just sits up there and puts my head down and reads my phone. No, you'll see me tomorrow. I'm circling around. I'm watching every single movement I can find. I don't just stand still. I don't put my head down and look at my phone or do some grading or whatever. No, I'm watching you like a hawk. I'm looking for a prey. The first thing I look for is your body language. The first movement is the body becomes tense. It becomes really tense. That's the first step to cheating. Your body starts to get tense. Because you know it's wrong. And your body is telling you, dude, this is wrong. It's giving you a warning system. It's wrong. Don't do it. After the tension, the fidgetiness becomes apparent. I'm telling you what I've seen in 30 years of teaching. It's not hard to find a cheater. Trust me. You give yourself away really quickly. Actually, you don't, but your body does. Okay, answer the question. What are the concepts that we used when I found the result? Go ahead. You have your hand kind of semi up, semi down. What is it? Huh? One, parallelogram. How did you get the result? I added vectors at the tail. Parallelogram rule, correct. Give me the second one. What? Huh? Equivalence. You took two forces, reduced it down to a single force, which was equivalent to the two forces it replaced. What's the third force? There's a third. What were the two things that you replaced into a result? What were they called? Force. Wasn't force one of our 12 concepts?
Yes.
So there are 3 concepts you use just in the first problem that you will do. Force, parallelogram rule, equivalence. You see how